Alright guys, I'm not seeing any more stragglers come through. If they do, we'll just let them come on in. Just give you guys an introduction of who I am, who I'm with. My name's Joshua Luters. Been with Little Fuse for about 4 years. Started off my time there working with our industrial fuses, elevator shunt trip disconnect switches, coordination panels, things like that. Transitioned over into sales engineering during that time. Before Little Fuse, I graduated with my bachelor's degree in engineering technology and worked as an industrial electrician. So I've been out in the field, I've seen some of the work practices, and have a little bit of hands-on experience with it. And today we're going to cover some arc flash material. So the first thing that we are going to cover today is going to be the actual anatomy of an arc flash. What is an arc flash? What happens during one. We're going to go over some of the arc flash hazard assessments and the codes that are there for that. We will also cover some changes that were made to IEEE 1584 back in 2018. We're not going to cover the 2021, but we're going to cover 2018 since that's what a lot of you guys will see out in the field. And then we'll cover some options that you have to reduce the incident energy in an arc flash, some different arc flash relay configurations. An arc flash relay is one of these methods that we're going to cover here. And then we'll go over a summary at the end. One thing that's not on the slides, and I'm going to do a little bit different than what you might see in another, or in a presentation somebody else might give, is going to be a view that's similar to like a return on investment. So how effective is the method that you're using for arc flash risk mitigation? How much does it cost? What's the integration like? Things like that. So you're going to kind of look at the system overall. So jumping right into the arc flash anatomy and what actually happens during an arc flash. So the first thing that you're going to see is going to be the electricity that is jumping between two conductors. An arc flash is essentially just the release of energy between two phases, and in this case that is air. Air is your impedance between those two phases. So with electricity being the first thing that goes, that means that light is going to be the first thing that's emitted. Shortly thereafter, you're going to have a lot of heat generated from the vaporization of copper. So that's going to actually form a plasma conductive material shortly over between these two phases. That can get very, very hot, about 20,000 degrees Celsius, depending on what your incident energy is, which is about 4 times the temperature of the surface of the sun. After that, you'll have your sound and pressure waves, and then you'll have any shrapnel that is actually coming from other material in the panel or anything that would be remaining of the bus bar. Shrapnel can come out of there at 700 miles an hour. A sound wave is about the stick of a dynamite. So overall, a pretty dangerous situation for both the equipment that's in there as well as the personnel. So speaking of equipment, the cost of an arc flash can be anywhere between $2.5 million to $3 million in damages. The way that you typically add up to that would be the damage to the material itself, the downtime, so the amount of time that you're losing for production and the time it takes to actually get this all cleaned up and replaced. Lost wages for any personnel who were involved in the incident, medical bills for any personnel, and lawsuits and litigation costs, especially if you're not up to standard, which I'll cover some of those later. So easily can add up to be an expensive thing. Obviously, personnel protection is what we're considered or concerned about most, but still important to factor in the cost. Generally, when we're talking about arc flashes, you'll hear the term incident energy used a lot, and you'll hear the term arcing current used a lot. Essentially, what arcing current is that's the amount of current that you have in the event. And incident energy is going to be your I squared T, or your current squared times your time that the arcing is occurring. The way that you actually calculate your arcing currents is dependent on your available short circuit, the bus gap, your electrode configuration. That's also tied in with your enclosure size and system voltages. And the way that you would get to your incident energy is by using that short circuit current that you looked at before, as well as the duration of time, and from that you can kind of determine what your working distance is. Now, just to cover some of these in a little bit more detail, the bus gap for 1584 did have some updates in the 2018 revision. They now have default values for 208 volt to 600 volts and 600 to 15 kV, so they do have spacing guidance and other guidance in there for that. And the electrode configurations were also updated in 1584. We're going to take a closer look at those later on. Just before I move on, because the next slide is relevant to this, the first thing that we can actually do about arc flashes is typically going to be this arc duration, which is why I have it highlighted here. You can see some of the other factors, like anything in this area, you'll see can actually be adjusted during the design phase. But once you are actually in the application, most arc flash mitigation methods try to interrupt as fast as possible to reduce against this. So this is your linear relationship between the amount of time that the arc continues on for versus the amount of energy that's released. So you'll see at 100 milliseconds we actually get to that cable fire point, which is probably the most dangerous point, because that's when you're going to start to get to your vaporization of copper and that heat energy released. The longer you let that go for, the worse it's going to get. Now, arc flash mitigation methods like relays open in about 1 millisecond, and then the circuit breaker is typically the longer acting. So you'll see a relay tied in with like a shunt trip circuit breaker or trip overcoil or voltage coil circuit breaker. This combination is well below that cable fire point, so you are mitigating it well before you actually get to that heat energy release. The hazard assessments themselves. So just before we actually get into some of that, 66% of the workforce has responded and said that their institute or the place that they work has not completed an arc flash assessment. So you're essentially working with some unknown variables. You don't know how dangerous your equipment actually is. And about 3/4 of respondents say they have equipment that's rated to 8 calories or more. So you're introducing quite a bit of room for error there if the PPE is faulty or if it's not equipped properly or anything like that. So just to keep that in mind. We're going to talk a little bit about some of the standards and what an arc flash hazard analysis is. Essentially what this is just a mathematical estimate of arc flash risk in your application. The way that is typically done is by using a standard, and the purpose for it is to identify everything here. So you're going to determine what your incident energy is that we talked about earlier, and then you're going to determine your working boundary. So that's going to be your arc flash protection boundary, and then your appropriate working distance, and then of course the calorie rating for your PPE. So calorie rating is essentially just the amount of heats per centimeter squared that's released during an arc flash. You'll see an arc flash expressed in calories. You'll also see PPE expressed in calories per centimeter squared. The official term for it is ATPV. You'll almost never really see that, especially if you're just going out and talking about it in commonplace. But the main thing that you want to consider here is just making sure that your PPE is rated to at least the calories that are available in the event of a fault. All right, some of the aforementioned regulations and standards. I'm sure everybody here is familiar with OSHA. OSHA, specifically 1910.132, is the required protocols for arc flash. This is based on guidance from the NEC, the NFPA 70E, and the IEEE standards. Speaking of the NFPA 70E, this is also one of your guiding regulation bodies. I do have CSA on here. I know most of you guys aren't worried about that since that's primarily a Canadian thing. But then we also have IEEE 1584, which is the guide for performing the actual hazard calculation itself. So this is going to provide your procedure on how to calculate what your hazard is. When you look at the electrical codes, this would be things like the NEC or CSA if you are in Canada. They are in place to provide a minimum bar of safety. So this is a minimum requirement. So this should be pretty much your electrical Bible. There are still some better standard industry practices that you can do out there, but this would be your minimum. As part of that minimum, I have actually gotten some articles pulled up here, specifically 110.16 from the NEC, which is for labeling. The labeling guidance here is going to show you the voltage, your incident energy value, your working distance, and your arc flash boundary. If any of you guys are electricians, I'm sure you're familiar with your limited approach. So that is the area where your qualified electricians can be within, and then your restricted approach, which is you're only one electrician actually doing the work on that equipment. You'll see the value for the restricted approach is typically much, much closer. You're actually working on the equipment, and your limited approach is a little bit further away, so if somebody has to get some tools ready or anything like that. This is that 110.16 in the NFPA 70E. This has to be visible and easy to read on your equipment. So it shouldn't be hidden on the side of it or tucked away in the back or damaged or scraped up. It does need to be readable so people can actually use that. This is kind of an example of what not to do. This doesn't really tell you anything. It says, okay, grab some PPE, but how do you know what PPE to get? So it is important to actually do the arc flash hazard analysis and determine all of this required information. I'm not sure how familiar everybody is with the hierarchy of controls. I get mixed results every time I ask this question. If I ask you, do you know what the hierarchy of controls is? Most of the time people say no, but it is right here on the cover of the NFPA 70E. Essentially what this is just the methods to reduce the risk in an application. Historically, there's been a large emphasis on these bottom three guys right here, which is your PPE, administrative controls, and your awareness. If we make this an automotive analogy, PPE is like your seat belts, administrative controls is like your traffic laws, and awareness would be your speed limit signs. Something we want to focus on today is going to be the top half of this pyramid, which would be your engineering controls, substitution, and the elimination of the incident altogether. So anything that we can do to take the onus out of the worker's hands and eliminate human error, the better. And I'll actually show you why that's important in a second. Before we get to that though, just going to cover some of the different iterations of the NFPA 70E. NFPA 70E has some comprehensive guides for establishing policies, practices, procedural requirements. This is all for electrical shock and for arc flash incidents. They have an electrical safety program that is requirement to be developed or implemented, and then they have a requirement for a risk assessment. You'll see this commonly talked about with establishing an electrically safe working condition, things like lockout tagouts, energized work permits, and then the actual performance of the risk assessment. Just going to jump into IEEE 1584. So IEEE 1584, which as mentioned before is your guidance for arc flash hazard calculations, was updated in 2018. The new revision is based on 1,800 actual tests, so they did perform a lot of tests to actually get a lot of this information. And they introduced three-phase voltages, 208 to now 15 kV, and they have this based on three voltage equations. So they have a 600 volts, a 2.7, and a 14.3. There are methods for interpolating anything that is not one of these direct voltages. They have now extended the bolted fault current, which is now dependent on voltage. So it used to be, well actually I don't have what it used to be, but what it is right now is 208 volt to 600 volts is going to land you somewhere in the range of 500 amps to 106 kA. 600 volts to 15 kV is going to land you somewhere in the range between 200 amps and 65 kA, and that's going to be dependent on some of the other factors that we looked at before. Last thing on here is the electrode gap, which is now dependent on your voltage. Speaking of the electrodes, there are different electrode configurations now in IEEE 1584. We're going to cover some of those in just a second, but just keep in mind that some of the incident energy in some of these is 3 times what it would be in some others, and I'll show you the reason for that. The enclosure correction factor also exists in here now. Standard opening is 20 inch by 20 inch. The maximum value is typically 49 inch by 49 inch. It's not completely based on the volume. There is a trend for larger openings. You'll have a larger incident energy, but the trend is actually reversed for a shallow enclosure. The smaller opening would be better for a shallow enclosure. The first electrode configuration we're going to cover is one that's probably most common, this in HCB. So this is your vertical conductors inside of a metal box. So essentially what you've got here is you've got 3 bus bars going from the bottom, or they can come from the top as shown here. In the event of an arc, what you're going to see is on the tip of the bus bar, or right across the tops here, you'll actually get your arcing between the phases, and then that's going to shoot your arc flash energy down, or in this case up. It's going to go towards the top of that enclosure. So it's not being sprayed directly at the worker, or being expelled directly out of the enclosure at least. The next one is the same bus bar configuration or conductor configuration, but it is now inside of an enclosure. So essentially what happens here is you've still got that same arcing going on, but now that enclosure is acting as a method to direct it directly out of the enclosure or at the personnel. HCB works on a very similar principle. This is when you've got your bus bars coming in most likely through the back of the enclosure. And again, that's going to be directly out of the enclosure because it is again going through the end of the bus bar. Vertical conductors in open air, you'll typically see this used on much larger industrial equipment. So it's too large to be contained within an enclosure. It's effectively acting as the same as a VCB, except for now you no longer have the enclosure to kind of keep the incident isolated. So this is just going to go straight out and around a little bit. And then HOA, which is your same principle as the HCB earlier. Okay, IEEE 1584 has 10 steps for actually performing an arc flash analysis. There's a lot here. I'm not going to cover everything. We do not have the time to get to everything else if I did. But essentially, just looking at your bolted fault currents, IEEE 551 and 3002.3 has guidance for your short circuit current analysis. The gap size is included within the 1584 standard. As mentioned, as we just talked about, the electrode configuration was updated from 2002, which just used to be an open air and box, but now we have all these different configurations that you need to factor in for good reason, because the way that energy is being expelled from the enclosure, or lack of an enclosure. The working distance is roughly the same as 2002, but it is now in a table format with defaults, and they do now have a 12-inch minimum working distance. So that is a new minimum that was instated in 2018. There is guidance for calculating the arc current. It is not always very straightforward. If you have something that's coming from a generator or from a motor, these time varying sources or time limited sources need to be factored in and can be a little bit more of a calculation. Determining your arc duration, this is considered to be the equivalent of your last overcurrent protection device, so fuse, breaker, whatever it is that you have for your overcurrent protection device. but generally speaking, they factor in a 2-second reasonable maximum. And then the incident energy, that's the location of your protected device. So is it immediately sitting on the line side of your equipment, or is that 20 feet away, or on another floor altogether, or wherever? The boundary is very similar compared to 2002, at least for low voltage, but for medium voltage, the boundaries are much shorter than 2002, which is, I suppose, a good thing, at least for a worker standpoint. And then I keep talking about performing this analysis. There are models that can be used for this, very commonly SKM, ETAP, Easy Power. There's a lot of electrical software that can do this. This is intended to be used by qualified personnel, so we don't want just anybody trying to punch their way through it. Different methods for incident energy mitigation. So the NEC 240.87 has 7 different approved methods for mitigating arc flash hazards. We're not going to take a look at every single one individually, but we are going to go over some of the actual mitigation methods that are used in the field. So this is going back to the human error, just before we move on into some of these mitigation methods. IEEE, the Gold Book, or they used to be referred to as the color books, does cover some of the different statistics on how faults are occurred. 46% is just from the environmental factors, and then about 30% is caused by human or animal error. So going back to that top half of that hierarchy of controls, if we can eliminate about 30% of those risks, then why not? This is going to tie into the next slide. So I know it seems a little out of place here, but essentially what I'm getting at is that about 95% of faults are line to ground. And then you'll see about 5% would either be phase to phase or 3-phase. Now it's not to say that these don't happen. 3-phase is typically going to be your bolted faults and will typically be caught well before startup. But phase to phase is often an escalation of line to ground, especially in ungrounded systems. So if you have an ungrounded system and you lose one of your phases, your voltage is going to rise on your other phases, and that's going to cause an insulation breakdown or chattering or things like that, and that's going to escalate over to a phase-to-phase fault. So speaking of the different grounding systems, which is why I bring this up, something that you'll start to see most commonly now, ungrounded systems is a bit of an old one, so I'm not going to talk about it too much. But you'll see a lot of solidly grounded systems right now. And essentially what happens here is as soon as you have a phase that goes to ground, you now have a low impedance to no impedance path for current, and that's going to have a very high incident energy or fault current. So one method that you can actually try to integrate into your system is by using a resistance ground. And essentially what this is you're placing a resistor on your ground. It be tapped into the ground or the neutral on your transformer. And this will be sized to limit the fault current. So you'll typically see this size to 25, 10, 5 amps, whatever it is. That sizing is usually determined on what your charging current would be used or be in the application, so you're not getting trip currents or things like that. But a very effective way to just eliminate the arc altogether is by using an NGR or HRG or high resistance ground or neutral grounding resistor. Okay, moving right along to the overcurrent protection. One common method is circuit breakers. When you start looking at circuit breakers for arc energy reduction, there are some caveats, most specifically for 1200 amps or higher. Something that's important to note here is that it says it can be adjusted to 1200 amps or higher. So if you've got something that's 800 to 1200 and you've got it set to 800, this still applies to you. Because if somebody comes along later on and they add something else to the system, they say, okay, well now we need to increase it to 1200. That needs to be already taken into account during the design phase. So essentially what that means is you're going to need to provide documentation that shows that this method is going to clear it within the specified time. And it's also going to mean that you're going to need to use one of these 7 methods that I referred to earlier from the NEC. ZSI, differential relays, or bus differential relays, energy maintenance, things like that. And I'll cover some of these in just a little bit. But you also need to do some performance testing. That's typically done by a manufacturer, or you can look at softwares like SKM, Easy Power, ETAP, things like that. Fuses, which is your other common form of overcurrent protection, are very similar in that 1200 amp line is where it's being drawn. Fuses, as we know, are not adjustable. They're just pieces of metal. So, this would apply to all fuses that are 1200 amps or higher. So you're going to need to have the documentation. So that would be documentation most likely covering a clearing curve or clearing I squared T. And then you're going to have the second stipulation here, which is specific to fuses. So you'll see this a lot on like class Ls, those real big guys, or in class Ts, which are your fast-acting fuses. But it is the requirement to clear within 0.07 seconds. If your fuse can do that, you do not have to use any of these 5 other methods. You can just bypass that altogether. That again is something that you can usually find from the manufacturer. Like we at Little Fuse have clearing curves and clearing I squared T available for most of our fuses. So if you can just identify the fuse, they can open properly for your application. Saves you a lot of trouble. Trick to that is, I'm not going to touch on that too much. The operating speed of the fuse is dependent on the amount of current that you have available. So the more current, the faster the fuse is going to operate. I'm going to just harp on this again for just one quick second. Again, hierarchy of controls is very important. I want to make sure people are aware of it. It's on the cover of the NFPA 70E. Try to focus on this top half of that triangle. But this is going to be kind of my transition here over to the return on investment, so to speak. So this would be, what is your cost of the design? Are you having to hire a consulting engineer? Do you need software? What is the actual cost of the design? The cost of the equipment. Do you need new breakers? Do you need new sensors? Do you need new wire? And then we'll probably put the installation costs and labor time in here as well. I'm sorry, or labor cost in here as well. Cost of downtime, which is how easy is it to install the equipment? Are you losing 4 hours? Are you losing 4 days? And then lastly, we'll talk about how effective the method is at actually reducing the calorie. First one, which is right near the top half of that hierarchy of controls, it's the second one that's on there, is substitution. So this is the actual idea that you're going to change a very large transformer here over into smaller transformers. This is something that you'll typically only do at the design phase, because as we know, transformers are very expensive, something to the tune of millions of dollars. So essentially what you're doing here is you're just you're cutting your instant energy effectively in half. Now if you can do this during the design phase, that's all the better. But again, the cost of the design is very high if you were to try to do this as a retrofit. Since you're completely changing your system, you're going to have to redesign everything. The cost of the equipment is very expensive since the transformers are not cheap. And again, you're going to have to rebuild all of your system architecture. Same thing goes for your downtime. If you're going to rebuild all your system architecture, that's going to take you a long time. But then the actual calorie reduction can be impactful because, like I said, you're effectively cutting it in half. But if you're still tapping off at 50 MVA and you've got something right here on the load side of it, you're still going to have a high enough fault to cause an arc flash. This is considered to be substitution because you're substituting out non-resistant switchgear, but you're not actually mitigating not actually mitigating the fault itself. So this is more of a risk mitigation and not a arc flash mitigation, which is substituting for the resistant switchgear. And essentially what's happening for arc resistant switchgear is the fault will still happen within the enclosure, but it'll be vented out either the side, top, bottom, or back. So it's just expelling that in another direction. Problem with this is if the door is open and somebody is working on it, then it's not going to do anything for you. It's still going to be directed at the nearest enclosure, and that is not going to really help. Also important to note here that this is not an approved method for NEC 240.87. You will still see this used a lot in the field as just an additional method to a lot of other things, but it is not an approved method by itself. The reason why a lot of places do this, though, is that the cost of the design is very low. You're just essentially replacing non-resistant gear with resistant gear. The cost of the equipment can be quite a bit more expensive. I don't have hard numbers for you, but just from anecdotal experience, it's usually about 4 times the cost of non-resistant gear, which is already not cheap. And then the cost of the downtime, so you're going to have to take everything out of here in the event that it's a retrofit, and then put it back in. So this can be a significant downtime. You're looking at several days. And then for the calorie reduction, there is no calorie reduction. You are just redirecting the arc itself. Zone selective interlocking or bus differential, commonly referred to as ZSI. These are very similar systems. Essentially what you're doing is you're monitoring at the beginning and you're monitoring at the end, and as long as you are reading the same, you're fine. But if you suddenly have a large inrush of current, then your system is able to say, okay, we need to interrupt everything. These are very effective methods, but they do require a lot of engineering resources on the front end, because you're going to need to make sure that you have your breakers both selected properly and the settings configured properly. In a retrofit application, ZSI and bus differential both require a lot of CTs and new breakers, either at some or all levels of your equipment, and that's going to mean modifying the breaker all the way back to the MCC or panel board level. I'm not sure if any of you guys have dealt with putting in new CTs, but sometimes they can be a pain to deal with, especially if you've already got everything wired up. Another caveat for the bus differential system is that it can interrupt any selective coordination that you have in place. So a lot of industries are now looking at selective coordination even where it's not an NEC requirement. Reason for this is even without an arc flash, if you just lose a fuse or you lose a breaker, you don't want to lose a lot of your other branches. That's going to cause a lot of unneeded downtime and be a lot harder to identify where your fault happened, things like that. So bus differential can actually bypass any selective coordination that you've done and just interrupt everything at a feeder level. So important to keep that in mind when we look at cost of downtime. So looking at the cost of the cost of the design, give me a second. I'm actually gonna get a drink of water. Okay, so cost of design is quite a bit high. Talked about the breakers, getting the requirements and the selection settings done. Cost of equipment, somewhere in the middle. If you're doing retrofit, it's going to be quite a bit of breakers, but breakers aren't the end of the world. The cost of downtime is probably also in the middle, again, somewhere. You do have to install those breakers. You do have to make sure the settings are done. You have to do the testing on it. And it can take multiple days, depending on what the complexity of your system is and how far up the chain that you actually have to go. And then the calorie reduction is pretty significant for both the methods. They are at least decent on that front. Arc flash relays. This is something that you'll see very commonly used in the workplace right now. So this is essentially watching for light. So if we talked about the anatomy at the beginning, we talked about how the electricity going across was the first thing that occurs. And as a result, the light of that electricity is going to be the first thing that comes across. So essentially what's happening here is a point sensor or a fiber optic cable is being used to monitor for that light. And it'll be above a certain lumen level, so you'll know for a fact that it would actually be an arc flash. This is a standalone piece of equipment, so you're not actually tying it into your electrical system. This is only watching for light for most of these. Some of them have some additional some features, and we can get into that a little bit later. But that means that you're not having to shut down your system and actually rework some of the architecture to install this. These are also easily integratable by SKM, Easy Power, ETAP, any of those modeling softwares that I mentioned before. All of these arc flash relays are already included in those modeling software, so it's very easy to punch in and say, okay, I've got 24 calories, now I've got 4, I can move about my day. So as a result, your cost of design is going to be very low. The cost of equipment is very low. Generally speaking, your arc flash relays and your sensor installation tends to be well underneath $10,000, which is much lower than some of the other ones that we've talked about. And the cost of downtime is very minimum. You're looking at typically about 4 hours to install the relay itself, along with the sensors, which means that even if you are doing a de-energized work, it's very quick. And the calorie reduction is very high on this. So we looked at that linear curve earlier. We're getting that cut off well before the cable fire points, and your calorie reduction is reduced significantly.
How many milliseconds does this clear the breaker?
So the relay itself is 1 millisecond. The rest of the time is dependent on your breaker, so the condition of your breaker, speed of your breaker. And that's typically about 35 to 60 milliseconds. Moving on down to administrative controls. We are now on the bottom half of that hierarchy of controls. It's something referred to as a maintenance mode switch or a maintenance mode breaker. This is it is approved by 240.87 for the NEC, but essentially what this is it's a switch that you need to place into the maintenance mode before you go in to start working on the panel. So this is watching for any overcurrent that goes above what your set value should be. Pros and cons. Pros, it's very, very fast. It is a very effective tool at reducing calorie reduction. As I mentioned earlier, any current that goes above where you're supposed to be will trip this unit. Cons, nuisance trips, and the other con here would be in the event that somebody does not read the label, that the label is damaged, that they are not, they just forget and they don't trip the switch. So if you've got somebody who's now working in that gear and they do not have that switched over, that means that they now have the full available incident energy. So if you had something that you were otherwise reducing from a 40 cal down to, let's go ahead and say 4 cal or 8 cal, and somebody's just wearing a long sleeve t-shirt or a long sleeve shirt in the pants, that's going to be very disastrous in the event that that switch is not used properly. The other thing that's a bit of a trade-off here is that the only time that you actually get this arc flash mitigation is when that switch is turned, meaning that even if the enclosure door is closed, so that you've got the moisture, so that 46% of faults that we looked at earlier, those environmental caused faults, or you've got a rodent or something that's in there, if that arc occurs and this is not arc resistant switchgear, you are still going to have that possibly damage the enclosure or damage everything else that's still inside there. Cost of design is very cheap. It's very easy to select these things. The cost of equipment is somewhere in the middle. You're just effectively replacing all of the breakers that you have in your system. And the cost of downtime is somewhere in the middle because you are going to have to replace all of those breakers. But as I mentioned earlier, calorie reduction is high, assuming it's being used properly and that the arc is only occurring when somebody has that switch turned.
That's just low voltage though, correct?
Most typically, yes. Yeah. PPE alone. This is in the hierarchy of controls. It is important, but this is a last line of defense. We were just having a conversation before we got started that, like workplace safety isn't always on the forefront in some locations, and that some facilities use this as an effective solution for arc flash hazards. It should be used as a last resort. These things can be damaged. Not all workers have as high of calorie ratings suits as needed because they are expensive to get. And you have to get them sized for everybody. So if you look at Kevin Hart and Shaq, they're not the same size people. You know, you have to get everybody their own suit. On top of that, the gloves that each worker needs to have needs to be replaced every 6 months, and those are about $70 a pop. So each worker that you've got, each pair of gloves every 6 months. Cost of design doesn't exist. Cost of equipment relatively low in the short term, but can add up over time when you look at just getting some of these other methods implemented and just removing its indefinitely. No downtime, no calorie reduction. Important to note here, since there's no calorie reduction, you are still going to have the cost of equipment if that equipment does end up damaged. I'm actually going to cover the arc flash relays in a little bit more specific, since that's what we at Little Fuse specialize in, and we'll cover some different configurations. Real quick, I'll just show you exactly what happens in the event of an arc. So let this thing charge up for a second. This is going to be a bit like a neuralizer from Men in Black, so don't look directly at it. But you'll see here that you've got your point sensors, and then you've got your breakers, and the relay is down in here. And that opens as soon as the light is detected on the point sensor. Now what you can do with that is you can wire it up into a couple different configurations. So first configuration here is going to be main tie main, and essentially what's happening is you've got this tie breaker that sits right in between your two main breakers. So in the event that you have a fault that occurs on the right hand side of this configuration, the relay that's on the right here will send a signal to this guy and to this guy. So your tie breaker is going to open and your main breaker is going to open, and that means that the left side of this configuration can continue to operate. An easier way to view that is on a single line diagram, something like this. You'll see here, this is your incoming feeder, your main breaker, and this is your bus tie. So assuming that your fault occurs somewhere down the line, it'll interrupt here and here, and your other half can continue to operate smoothly. There are two typical sensors that you'll see used with arc flash relays. You'll see point sensors, which is what we have, the blinky guys there, and then you'll see a fiber optic sensor, which is that string that runs across the top. The point sensor is a 6-foot cone that extends out, and it's about 12 feet wide. You'll see this oftentimes used in panel boards and MCC buckets, anywhere where you have a tight fit. And for fiber optic cable, this actually monitors for light along the entire length of the fiber optic portion of it. So this is very good for in the event that you have a bus bar that you want to monitor along the length of it, or if you have an enclosure with a lot of obstacles and things like that where you don't want to have 6 different point sensors in there, you can just run a fiber optic cable through it, and I'll actually show you a picture of that in just a minute. Some of the features that you'll see oftentimes used with these light sensors is the light that you'll see flashing, which tells you that the sensor is still good, it's in good health. There is a built-in circuit check, so you'll see that there's 4 wires here. One of these is going to go back to the relay and tell it that it is okay, that this sensor has not been damaged, or the line going between the sensor and the relay itself has not been damaged. They can both be extended, both the fiber optic and the point sensor can be extended up to 50 meters, and they do have an easy plug-in connector, which means that you guys don't have to splice this and spend a whole bunch of time trying to get everything wired in individually. It's just an easy plug-in connector. Okay, so what happens in the event of a standard configuration where you've just got your breaker and you've got your upstream breaker and so on and so on? What happens if there is a failure? Let's go ahead and say you've got an arc flash over here, and this light sensor detects it. That is going to send a signal to this guy here. It's going to send which is your relay. Your relay is going to send the signal out to your shunt trip breaker. If that breaker malfunctions, or if there's an issue with this equipment or this equipment, what it will do is send an auxiliary signal out to the feeder breaker. And then, ideally you won't have a fault there as well. The odds of that are very minimum. So we've got a redundant safety feature built in here. Something I said that some of these relays have some additional features. I'm not going to go on a wholesaling pitch, but some arc flash relays like our PGR 8800 do also have the ability to have a CT wired in, and that will just detect the loss of currents, just detecting unit health here. As well as prevents nuisance trip. So if you've got, let's go ahead and say a very dark enclosure normally, and then you open up and it's a bright sunny day out in Arizona, you don't want that to trip the relay. Now it does have to be above a certain lumen level anyways, but the CT is just an added level of nuisance protection. Okay, so I mentioned redundant features in terms of the auxiliary contact and the CT. There are some other redundant features that are included here. First things first, the sensors that I mentioned, they are sending back continuity. Specifically on fiber optic, what you'll see here is that you've got a transformer and you've got a transmitter and then you've got a receiver. If anything in this path or anything goes wrong here, that would cause the system to trip. The added CTs from the bright light that I mentioned. There's a solid states operation. And then the trip coil voltage being monitored constantly. Think of this as a kill switch if you're operating like a gantry or something heavy where you're constantly holding it in the on position. As long as you've got control power here, this contact is being held into position. So if the microprocessor on this thing gets damaged, if the unit itself gets hit with a forklift, or there's an arc flash in the enclosure that this thing exists in, or same thing goes back to those sensors, it'll automatically release that voltage, and then that's where you get your tripping. Just to show you how these sensors are typically installed, in this case we've got some sticky backs, but there's also other ways of getting this cable put into place. The sensor itself is panel mounted, so you'll see that there's actually a screw going into the panel here. Commonly used in transformer and substation installations, specifically this unit because of some of the redundant features that it has and the capability it has with the CTs. This is the fiber optic sensor that I referred to earlier. You do want to watch for a bend radius of 5 centimeters, but see how this heavy duty contactor might obscure the light. Let's go ahead and say you've got something over here. If you've got your point sensor here, it might not detect that. So go ahead and use a fiber optic cable to route along the entire side and bottom of the enclosure, as well as along the length of the bus bar that I mentioned earlier. And this is another way that that I alluded to, that you can actually get some of these wired in. Some common applications, switchgear and MCC. You'll see the point sensors used a lot here. Repairs for these equipment, or these pieces of equipment, can get pretty costly and are very tight in terms of space. So it's a great way to get retrofits taken care of. And wind turbine applications. So these are kind of tricky. They are such sensitive pieces of equipment that any contaminants that are in there or anything that's large enough to affect the impedance of the air gap that's within there can actually start to mess with the other equipment. So using something like a point sensor or fiber optic cable is very helpful for that. Just a quick recap of what we talked about today, which is how arc flashes are caused, different standards that are used for arc flash hazard assessments, changes that were made to the 2018 IEEE 1584, options to reduce your incident energy. And then just focusing on that upper half of the hierarchy of controls. If you guys want to know more about this, always feel free to reach out to me. Otherwise, littlefuse.com has articles on industrial safety and arc flash. And then we also have a technical resource section on our homepage for littlefuse.com. Other than that, does anybody have any questions?
For the arc flash relays, I guess, what's the maintenance like for that? What's the recommended maintenance?
So you typically don't have to perform any maintenance unless you notice that the unit itself becomes faulty. So they, 10 years, 15 years without any incident typically. Yeah.
And then for like a retrofit application, say like on an MCC, I guess who would install it then? Like the recommended contractors that?
Yes. Yeah. So this would just be your standard electrical contractor, whoever your electrician is at the facility. They're very straightforward. Something I didn't touch on is there's also Ethernet and like Modbus communication, SCADA, so it can be tied into the rest of your system to notify. There's multiple outputs, so if you want to have like emergency lights kick on at the same time that you have, there's a lot of other functionality, but all of that should be within the scope of a standard electrician. And if they have questions, they can reach out to us and my team here, and we can walk them through it.
Hey Josh, if I can interject, if anybody has one line of category 3, 4 dangerous, send that to any of the CD Mosbach guys, and we can model that for you by putting this relay in there. And then typically we come out into the field and help do that installation, and we'll do the point placement with you guys. We're not electricians, we're just the manufacturer's rep, but we'll help you guys and say, hey, don't put that here or put this up above, and kind of direct on where that goes on the first time. But the main thing is, if you have a category 3, 4 dangerous, get the modeling done and say, how can we reduce this hazard? And if you can get that down to a category 1 or 2, why wouldn't you do it? That's the biggest part I would say out of this whole takeaway.
Yeah, absolutely.
Is the fiber termination done in the field, or is it?
Yes.
transfer received?
Yep. It's just plug-in connectors. As long as they're not exceeding that 5 centimeter bin radius, it's not going to break on you.
Stands are already made, like.
Yes.
Polish any glass. Nobody's going to be polishing glass with fiber ends. It's already
Yes.
pre-done. There's preset lengths in there, and it's retrofitted into any system that's out there. Eaton, Siemens, Square D, it doesn't matter what gear, because there's predetermined lengths. Josh, what are the lengths on that cable?
It's like 8 meter, 16 meter, and then you can get additions to extend it up to 50 meters. But when you extend it, it's just another plug-in. You're not cutting glass, and it's the actual extension for it is the actual copper portion. The fiber optic is only the part that you'd use in the enclosure itself. Anybody else have any questions this morning? I'll take that as a no. All right, guys. Thanks for stopping by.